Events of the KT boundary, more than an impact. Geological time is separated based on stratigraphy and various dating methods, such as radiometric dating. The Cretaceous-Tertiary KT boundary, also known as the Cretaceous-Paleogene KPG boundary, is found at approximately 66 million years ago, according to radiometric dating. This is known as when the dinosaurs went extinct. It's the most recent of the Big Five mass extinctions: the End Cretaceous mass extinction, End Triassic, End Permian, Late Devonian, and Late Ordovician. Here's an image of the KT boundary. The initial proposed cause for the extinction of the dinosaurs was suggested to be a nearby supernova event by Russell and Tucker in 1971, which might have caused the extinction of many animals, including dinosaurs. In 1980, Alvarez et al. Put forth the impact hypothesis. Iridium is considered extraterrestrial, but it was concluded to not be from a nearby supernova due to a lack of plutonium isotopes found in the layer. Quote, "Reasons are given to indicate that this iridium is of extraterrestrial origin, but did not come from a nearby supernova. A hypothesis is suggested which accounts for the extinctions and the iridium observations. Impact of a large Earth-crossing asteroid would inject about 60 times the object's mass into the atmosphere as pulverized rock." Chicxulub was later proposed as the impact site by Hildebrand et al. In 1991. As described by Mittal et al., in a surprising coincidence, the End Cretaceous KPG boundary microfaunal extinction also corresponds precisely in time to what may have been the largest meteor impact of the past billion years of Earth's history, the Chicxulub crater at 66.05 MA. The Deccan Trap's eruptions were underway well before KPG Chicxulub time and are most likely the result of the mantle plume head that initiated the presently active Réunion hotspot track. Thus, the Deccan Traps were clearly not generated fundamentally by the impact. Deccan Trap volcanism was not continuous and spiked after 66.052 million years, where 50 to 75% of the lava volume occurred after this mark. Described again by Sprain et al., the eruptive tempo of Deccan volcanism in relation to the Cretaceous-Paleogene boundary. Late Cretaceous records of environmental change suggest that Deccan Traps volcanism contributed to the Cretaceous-Paleogene boundary ecosystem crisis. Nor is Chicxulub the only KT boundary impact. The Nader crater, discovered offshore of Western Africa, has a stratigraphic framework suggesting that the crater formed at or near the Cretaceous-Paleogene boundary, approximately the same age as the Chicxulub impact crater. As described by Nicholson et al., the Nader crater is situated at or very near the KPG boundary, based on our seismic stratigraphic framework for the Guinea Plateau and that of previous studies. This suggests that the Nader crater, if confirmed as an impact crater, approximately coincides with the Chicxulub event in Mexico. This potential temporal coincidence with the Chicxulub event in Mexico leaves open a number of possibilities, including that 1. The Nader impact may have been part of a binary asteroid or have formed by partial breakup of the larger Chicxulub asteroid that led to the major KPG extinction event, or 2, it may have been part of a longer-lived impact cluster, or 3, may be causally unrelated to Chicxulub. Here we see the central uplift of Nader crater, as well as what has been termed a seismic pull-up processing artifact, curiously flowing with the crater itself. Then there is the Baltish crater, another end-time Cretaceous impact. Comprehensive argon-argon dating of a range of melt samples yields a mean age of 65.17 plus or minus 0.64 MA, within errors of the KT boundary. Their proximity does raise the important question of how many impacts there might have been close to the KT boundary. The Shiva structure, a possible KT boundary impact crater on the western shelf of India, is believed to have formed around 65 million years at the KT boundary. The Tefe River structure shows geophysical evidence of a possible impact structure at the KT boundary in Brazil. The Silver Pit crater, whose structure affects Cretaceous chalk and Jurassic shales and is well preserved below several hundred meters of post-impact tertiary strata, which constrains its age to be 60 to 65 million years old. The Jebel Hadid structure in Libya. The age of the structure is probably post-early Cretaceous to pre-Pliocene, bears a strong morphological resemblance to the impact structure of Tin Biter in Algeria. The age of the Tin Biter impact is poorly constrained to less than 66 million years by stratigraphy, the youngest geological unit affected by the event being the approximately 66 million year old Maastrichtian limestones. Kara-Ust-Kara twin impacts. It has been suggested that the Kara impact event may be associated with the KT boundary event. Previously reported potassium-argon ages showed wide margins of uncertainty and clustered around 60 million years, while more recent potassium-argon determinations seem to support an association with the KT boundary. Our own analysis of several argon 4039 age spectra, however, indicate an age of greater than 70 million for the Kara impact event, perhaps close to the age of the Campanian-Maastrichtian boundary. Even if there is no association with the KT boundary event, a double impact leading to craters of approximately 65 and 80 kilometers diameter must have been an important geological event with possible global significance. If of impact origin, the age of the Omeonga structure can be constrained to late Cretaceous Cenozoic according to the youngest units in which the ring structure was formed. Magnetic fields associated with a probable late Cretaceous astrobloom at Dumas, Saskatchewan. In addition, major steps in orogenies also were occurring. In the Himalayas, collisional events began with collision of India and the Trans-Tethyan subduction zone in late Cretaceous to early Paleocene time, followed by the collision of India plus Trans-Tethyan ophiolites with Eurasia in mid-Eocene time. Additionally, volcanic rocks in southern Tibet dated to 66 to 63 million years. In the Western Alps, grains having apparent ages up to 66 million years were determined in crystal cores by in situ laser probe analysis, while ages as young as 45 million are typical of the crystal rims. Another study in the Western Alps shows characterization of metamorphism conditions under which diagnostic mineral fabrics were formed, thereby linking the strain history with the PT evolution. Isotopic dating of minerals, which could be related to specific segments of the PT deformation path to define the age of the high-pressure metamorphic peak and rates of subsequent exhumation, which might be related to regional tectonics. The uranium-lead age of Sveen at 66 million years is most likely to record an age during the high-pressure event, although the exact point on the PT path is poorly defined at present. Magmatic and metamorphic ages in the Cessia zone of Western Alps were analyzed. The Cretaceous ages constrain the timing of the high-pressure metamorphic stage. As shown, magmatism occurred first, starting in the Devonian, with metasomatism occurring through the Triassic, concluding with metamorphism across the KT boundary. In the Laramide orogeny of the Rockies, Bighorn Mountains shows a main phase of uplift and exhumation of the range occurred in the latest Cretaceous and early Triassic. Critical events for the generation of Cordilleran gold provinces specifically included the 66 million year onset of dextral slip on northern splays of the Borden Ranges fault system in the Willow Creek district, the 66 million year initiation of a transpressive regime, and dextral slip along splays of the Yalacum fault system within the Bridge River district. Paleomagnetic results from late Cretaceous welded tuffs in the Kissen group from the Sikhot-Allen mountain range have declination that indicate that the Sikhot-Allen block has rotated counterclockwise by 41 degrees plus or minus 16 degrees with respect to the Eurasian continent between late Cretaceous times and 53 to 50 million years ago. The data is interpreted in terms of a strong net horizontal force towards the ocean side acting on the lithosphere at the eastern margin of the Asian continent between the late Cretaceous and 53 to 50 million years ago. In the Saurashtra region of the northwestern Deccan Traps continental flood basalt province, India, Tholitic lavas have been intruded by the approximately 66 million year old Mount Gurnar plutonic complex, which comprises olivine gabbros, diorites, and monzonites profusely intruded by dikes and veins of void-bearing cyanites and lamprophyres. Silicic alkaline complexes of Alec, Barda, Gurnar, Rajula, and Fanai Mata were determined to all be placed coevally with the main phase of Deccan Trap volcanism 66.2 to 65.7 million years ago. Additional events at the KT boundary. South Central America is a region characterized by a long-lived intra-oceanic subduction zone with a volcanic arc active since the late Cretaceous. It displays many characteristics of zones where epithermal, porphyry copper, and volcanogenic massive sulfide deposits are found around convergent plate boundaries. At 67 to 65 million years, minor quartz porphyry dikes were emplaced into central and eastern parts of the rejuvenated fracture system of the Greater Butte region of Montana. Moeraki boulders of New Zealand are from the late Cretaceous through Paleocene. As described by Coulson and Vetter, the central and western Solomon Islands are composed of an exceptionally thick succession of lower Cretaceous to Holocene rocks. On the origin of the islands, they state Cretaceous and early Tertiary oceanic basement rocks, generally lacking terragenous material and extensively metamorphosed, contrast with overlying predominantly volcaniclastic sequences that are characterized by abrupt facies changes and relatively simple deformation. On the relative motion between North America and South America, according to Serrano et al., relative motion between North and South America, with at least a component of divergence, continued until approximately 66 million years ago. In the formation of the land bridge of Panama, with respect to the initiation of subduction zone magmatism at 66 million years, Warner et al. say it is interesting to note that the accretion of seamounts from the Galapagos hotspot track commences at 66 million years. Oakey and Chalmers describe the opening of the Labrador margin between North America and Greenland as follows. They considered that there were 4 distinct tectonic episodes for the region: rifting and basin development with volcanic intrusions during the late Cretaceous, sinistral faulting and regional uplift during the Paleocene, folding and thrusting during the Eocene, and post-orogenic collapse with localized normal faulting and salt diaparism, as described by Oshomoji et al. Previous works on the paleogeography of marginal basins along the southern Atlantic show that the Maastrichtian, between 72 and 66 million years ago, was dominated by brief continental flooding and re-establishment of the Trans-Saharan Seaway. Marine flooding also occurred in southern Wyoming during the Paleocene. In the formation of the Argentine margin, Rodriguez et al. Described the process as having a first pre-drift stage from 125 to 89.8 million years ago, followed by an onset stage from 89.8 to 81 million years ago, with a growth stage from 81 to 66 million years ago, concluding in a burial stage starting at 66 million years, that marks the cessation of the mixed system in the Paleocene due to bottom current intensification and transition to a pure contourite system which persists until the present day. Rhea and Janicek describe the wind-blown dust preserved in deep-sea sediment that can provide a direct historical record of global atmospheric circulation. Data from a reasonably complete Upper Cretaceous section of pelagic sediments recovered in the central North Pacific provides a good record of Aeolian activity during the time period between about 112 and 66 million years ago. The oldest seamounts of the Louisville seamount chain are dated to the late Cretaceous. As described by Michael Heads, it is clear that New Caledonia was deeply submerged. The main evidence for marine flooding in New Caledonia is provided by pelagic sedimentary rocks dated as late Cretaceous to late Eocene. As described by Seton et al., the mean age of oceanic crust is 64.2 million years, with the Pacific Ocean 65.7 million years, the Atlantic 69.2, and the Indian 60 million years, with the marginal and back arc basins having an average age of 47.8 million years.